In this video, we're going to look at chapters 5 and 8, not all of these chapters, but a large part of them. We're going to look at value static analysis and the envelope theorem. And we're going to begin with the usual problem of constrained utility maximization, where we maximize the utility as a function of Q1 and Q2, subject to our budget constraint where M is income or budget, and it's equal to the price of 1 times Q1 plus the price of 2 times the amount of Q2 that's purchased. By substitution, we can find that Q2 is a function of Q1, and that's an important thing here, because then we write M over P2 minus P1 over P2 Q1. So Q2 is a function of M, P2, P1, and Q1. This is not a demand curve, remind you. Therefore, when we take the total derivatives, we find that dQ2 over dQ1, which is just the slope of the indifference curve, is equal to, at the optimum, the negative of the price ratio of P1 to P2. Then we write the utility function as a function of Q1 and Q2, recalling or remembering as we go along that Q2 is a function of Q1. The first order condition then is the du dQ1 is equal to marginal utility of 1 plus the marginal utility of 2 multiplied by dQ2 dQ1. And we set that equal to 0 because we want to stay on the same utility function. We substitute for the dQ2 over dQ1, that derivative, we substitute this value up here, and we then get the marginal utility of 1 minus the price ratio times the marginal utility of 2, and when we rewrite that, we get our old result back where the ratio of the marginal utility of 1 to 2 is equal to the ratio of prices P1 to P2. Now the second order condition, we take the second derivative of the utility function with respect to Q2, and we get the first derivative of marginal utility with respect to 1. Then we get the marginal utility of 1 with respect to 2, and multiply that by that derivative dQ2 over dQ1 plus the marginal utility of 2 times the second derivative of Q2 with respect to Q1 plus the marginal utility of 2 with respect to dQ2, and multiplied by the slope of the indifference curve squared plus the marginal utility of 2, taking the derivative of the marginal utility of 2 with respect to good 1, times the slope of that indifference curve. And that must be less than 0 for a maximum. So we can rewrite that as follows, and I'm not going to go through that. You can look at that yourself. Then we make a substitution. In particular, we make this substitution that the slope of the indifference curve, we substitute minus P1 over P2, which is equal to the negative of the ratio of the marginal utilities. And we also know that d squared Q2 with respect to, so the second derivative of Q2 with respect to Q1, it has to be 0. And we can see that from this expression there. All right, once we've made that substitution, and we now factor out 1 over U2 squared, and we work through the mathematics, which you can look through in more detail, we get this expression that 1 over the square of the marginal utility of 2 has to be multiplied by this expression in brackets. And we've seen a very similar expression to that when we talked about production in one of the earlier videos, where we had, instead of the U's, we had F's for the production function. And again, this must be negative for the second order condition to hold, which has to be that the the second derivative of the utility function with respect to Q1 has to be less than 0. All right, and why does that have to be negative? Well, this term 1 over u2 squared is positive. We get the same result if we use the Lagrangian method. The Lagrangian in this case is just the objective function plus lambda, the Lagrange multiplier, multiplied by m minus p1 q1 minus p2 q2. We find that lambda is equal to the ratio of the marginal utility of 1 to the price of 1, which equals to the marginal utility of 2 divided by the price of 2. And then we get the ratio of the marginal utilities equals the ratio of the prices, as we did just above here. Way up here, okay, here. So, given that, we basically have the same results. And when we solve this particular problem, we get Q1 star, where the star, recall, means an optimum, is a function of price 1, price 2, and this budget or income. And the same thing with the second Q star is also a function of the prices and income, and is the lambda. The optimal value of the lambda is P1, P2, and M. So Q1 star and Q2 star are the Marshallian or ordinary demand functions. So we're going to substitute Q1 star and Q2 star into the utility function, and that gives us this expression here, that U star is a function of the two prices and of income. And we refer to this as the indirect utility function, because the function is no longer a function of the goods that we consume, but it's a function of the prices of those goods and the budget. Now, we can differentiate that indirect utility function with respect to the income, and when we do that, we get this expression here. And that expression says that the marginal utility of good 1 multiplied by the partial of the of the ordinary demand function with respect to income plus the marginal utility of 2 times the partial derivative of the ordinary demand function for 2 with respect to income. So that's what the partial of the utility function with respect to income works out to be. So from the first order conditions, we know that the marginal utility of 1 is equal to lambda star times P1, and the same for the marginal utility of 2, it's equal to lambda star times P2. So if we take the derivative of the indirect utility function with respect to M, we get this expression here, and that expression comes because we've substituted for the marginal utilities this lambda star times whatever the price of that good is. And we can regroup that, so we end up with lambda star times P1 times the derivative of the Marshallian demand function with respect to M, the Marshallian demand for good 1, plus P2 times the derivative of the Marshallian demand for Q2 with respect to M. Now recall our budget constraint, which is this, and upon substituting, we can differentiate with respect to M, to the income, and we get, for M, we get d partial of M over the partial of M with respect to M minus P1 dQ1 star over M, partial of M, minus P2 times the partial derivative of the second ordinary demand function with respect to income, and we set that equal to 0, which then leads to this result here. And where does this come from? Well, it comes from this part up here. So these things that are underlined in blue are the same, and so we've got this, and this is equal to 1 from this, because partial of M with respect to M is equal to 1, and we've just regrouped it so that this is on the left-hand side. So we get this. So if we go back here, this is 1. So then the partial of the indirect utility function with respect to M is simply equal to the marginal utility of income. Now let's take as an example this simple Cobb-Douglas utility function, which we had done before, and we showed at that time that Q1 star, the Marshallian demand for 1 is equal to M over 2P1. For 2, it's M over 2P2, and then for the optimum lambda or Lagrange multiplier, it's M over 2 times P1 times P2. The indirect utility function, as a result, is equal to U star Q1, Q2. We substitute these values that we found for the ordinary demand functions into that utility function, and we get that U star, the indirect utility function, is equal to M squared over 4P1, P2. If we take the derivative of the indirect utility function with respect to the income, we get that 1/2 M over P1, P2 is equal to this lambda star. All right, which is up here, which we showed earlier. So we take the derivative of that indirect utility function and we come up with lambda star, which is, of course, our marginal utility of income. So let's let M equal 100, P1 10, and P2 equal 5. Then we find that Q1 star is equal to 5, Q2 star is equal to 10, and this lambda star is equal to 1 as required way up here. All right, let's look at labor-leisure choice, where we assume that M is our money income, R is leisure, L is labor time, T is our total time, W is our wage rate. So we want to maximize utility as a function of income that we earn so we can spend it on things, and our leisure time. But we have a constraint that the total time, T, is comprised of labor time and leisure time. And we have a constraint that the amount of income that we have available is equal to the wage rate times the amount of time we spend on labor. And from that we know that labor is equal to M over the wage rate. So there are two ways that we can solve this particular problem. One is through substitution. So we start with T is equal to M over W plus R. Where does that come from? Well, it's labor, which is M over W plus R. And then we have that the budget is a function of R, and it's equal to the wage times T minus R. Remember, T is a fixed number like 24 hours. We take the first derivative of the budget line of the budget with respect to leisure time, and that's equal to minus the wage rate, which is the opportunity cost of leisure. We substitute M into U, and we get that utility is a function of income, which is a function of leisure time, and utility is a function of leisure time itself. So if we take the total derivative of du dr, we then get that marginal utility of income times the derivative of the income function with respect to leisure time plus the utility of leisure has to equal 0. This implies that the marginal utility of income is a function of, is multiplied by the negative wage plus the marginal utility of leisure time is equal to 0. And as a result, we find that the wage is equal to the marginal utility of leisure time divided by the marginal utility of income. And this is the marginal rate of substitution between money, income, and leisure. It's the slope of the indifference curve. And that indifference curve is given over here. and this is the optimal solution. So we have this budget line, which is this one, or constraint line rather, where this is time times the wage rate. So this is the maximum income you could earn if you were to take all your time and work at a wage rate of W. And this is your total time which is available. So if you had all of your leisure, you did no work, then you'd end up at this point. Now this utility, this indifference function, this indifference curve rather, should intersect the m-axes. Why? Well, the reason is rather simple. You cannot live on without any income. You have to have some kind of income, some amount of income. You can do without leisure, and that implies that this indifference curve does not need to intersect the leisure line, but it does need to, somewhere up here, intersect the income line. You need some money to live. And the reason is you've got other indifference curves through here which look like these here. Okay, so you'd have one that ran like this. Okay, it would need to intersect that line. So now we take the second derivative of the utility with respect to R, and we get this result here. We get this result, and it has to be less than 0. And we require that the second derivative of income with respect to R has to be 0, and that's because of the way that this constraint is set up. All right, so the second derivative of m with respect to R is 0. So then we get this result here, that the second derivative of u with respect to R is given by this more complicated expression, which we rewrite as the second derivative of the marginal utility with respect to leisure, the first derivative of that with respect to R minus 2 times the wage times the marginal utility of income with respect to R, the derivative of the marginal utility of income with respect to R, plus the wage rate squared times the derivative of the marginal utility of income with respect to income. Given the first order condition that the wage rate is given by the ratio of the marginal utility of leisure divided by the marginal utility of income, and after factoring out 1 over um squared, we get this result here, and it's identical in terms of how it looks as what we've had before. So this expression has to be less than or equal to, or pardon me, it has to be less than 0. So that means that these may or may not be positive or negative. They tend to be negative, right? A declining marginal utility of income and a declining marginal utility of leisure. But we don't know what this expression is going to look like. So these terms are likely negative, but we're not sure if this term is negative or positive once we work it out. And that's going to determine whether or not the second order conditions hold. Now, the second approach to solving this problem is to set up a Lagrangian as follows. This is our Lagrangian. This is our budget constraint written a little bit different, so that labor is equal to m divided by w, the wage rate. First order conditions lead to this expression where the wage rate is equal to marginal utility of leisure divided by the marginal utility of income, which we saw above, plus this constraint has to hold. Solving the first order conditions, we get that income is a function of time and w, and time is probably fixed, and that leisure is also a function of t and w. So then the indirect utility function, because these were the optimum values that we find, the indirect utility function is then a function of m star and r star, where these are given up here. All right, taking the first derivative of that indirect utility function with respect to time, total time, we get this expression where marginal utility of income is multiplied by the partial derivative of the budget with respect to total time, and we add to that the marginal utility of leisure time multiplied by the partial derivative of leisure with respect to total time. And when we work that through, we make this substitution here, and that comes from, these substitutions come from this expression for lambda. Okay, so we make that one based on this relationship, and this star is based on this lambda equals mu r, ur. And we get that that's equal to lambda star multiplied by this term here. Now, we differentiate the budget constraint with respect to t, and we get this expression here, and we set that equal to 0. This is a 1, which we move to the right-hand side, and these we move over as well, so we end up with this expression. Notice that this expression here is simply this expression here, and what happens as a result is we get this expression there, that the partial of the indirect utility function with respect to total time is equal to the lambda star. We then find the equilibrium value of labor by substituting r star, so the optimum leisure time, into the constraint that total time is equal to labor time plus leisure time, or we can find that by substituting m star into the function or the expression for labor time, m over w. In any event, the optimum labor function is t minus the optimum leisure time is equal to m star over w, the wage rate. All right, then we can define the envelope theorem. The envelope theorem simply says that the partial derivative of the indirect objective function, whether that's an indirect utility function as a function of Q1, Q2, or an indirect utility function as a function of labor time or leisure time and income, we take the partial derivative of the indirect objective function with respect to a parameter, and that's equal to the partial derivative of the direct objective function with respect to the same parameter evaluated at the optimum. Consider two examples here that we've already looked at. One is where we have a Lagrangian as a function of the utility of purchasing goods Q1 and Q2 plus the lambda multiplied by the constraint, or number 2, where we're looking at leisure time, and the Lagrangian in that case is equal to this expression. Utility is a function of income and leisure plus lambda multiplied by this constraint, t minus m over wage rate minus r, and we've already incorporated, through this expression, we've already incorporated the second, if you like, constraint, which was the budget constraint, that m is equal to WL, where L in this case is time spent in labor. So for the first Lagrangian, and if we take the partial derivative of that Lagrangian with respect to m, we get lambda star, which is simply the partial derivative of the Lagrangian with respect to m. So this tells you that this is the direct objective function, this is the indirect. All right, the second case where we looked at labor-leisure choice, we have that partial of the utility function, the indirect utility function with respect to time is equal to lambda star, which is equal to the partial of the Lagrangian with respect to time. So this is the direct objective function there on the right and the indirect utility function on the left. Now, the envelope theorem also applies to unconstrained optimization, and the best example of unconstrained optimization is the profit function, where profit is equal to the price times the production function, which here is a function of capital and labor, minus the rate of return, or the rate of capital, minus the wage rate times labor. We find that the indirect, or the optimum rather, pi star is equal to P times the production function as a function of the optimal K and labor, where K star is a function of P, R, and W, and labor is a function of output price, the input price for capital and the input price for labor, minus R, the input price of capital, times the optimum amount of capital, minus the wage rate times the optimum amount of labor. Take the first derivative of pi star with respect to, and here pi star, because we've substituted in the optimums, is equal to the indirect profit function. So keep that in mind. This is the indirect profit function. If we take the derivative of the indirect profit function with respect to the price of capital, if you like, then we get price times the marginal product of capital times the partial of the derived demand. That's what this is. These are derived demand functions, derived demand of capital with respect to the price of capital plus the price of output times the marginal product of labor multiplied by the partial of the derived demand for labor with respect to R as well, because we're going through R, minus R times partial of the derived demand for capital with respect to R plus K star, the derived demand for capital, minus the wage rate times the first derivative of the derived demand for labor with respect to the price of capital, of the input capital. Collecting terms, we then get this expression here multiplied by the partial of K with respect to R. But notice that P times F of K, recall that this is the value of the marginal product, and the value of the marginal product in equilibrium must be equal to the input price. So this is 0. Likewise, this term here, this is 0 because of the value of the marginal product of labor is equal to the wage rate. So when we bring the wage rate to the left-hand side, we get 0 on the right-hand side, so equals 0 by these first-order conditions. So what we're left with is this expression here, that the partial of the indirect profit function with respect to input R is equal to minus K star. Now, immediately you can think, if it's the partial of pi star with respect to R, then the partial of pi star with respect to the wage rate should give you the same kind of result, but in this case it should be that it's minus L star. And that's exactly what we find down here. All right, so we find that the partial of the indirect profit function with respect to the price of capital is equal to minus the derived demand for capital in an optimum, and likewise the partial with respect to the wage rate, the partial of the indirect profit function with respect to the wage rate is also equal to minus the derived demand for labor in this case. Now, if we differentiate this expression with respect to the wage rate, we get minus partial of the derived demand for capital with respect to the wage rate. Same thing here, if we take the partial of the wage rate with respect to R, we get minus the partial of the derived demand for labor with respect to R. And by Young's theorem, we find that the pi star with respect to W and R is equal to pi star with respect to RW. That's basically what Young's theorem says. And what that means is that the partial of the derived demand for labor in an optimum with respect to the capital input price is equal to the partial of the derived demand for capital, the optimum derived demand for capital with respect to the wage for labor. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.